Hello everyone. We have now thoroughly covered the system that ensures the drone's physical safety, its ability to avoid obstacles and maintain stability. But in our modern connected world, physical security is only half the battle. We must also secure these devices from digital threat. This begins us to the critical topic of cybersecurity vulnerability in drone network. The fundamental issue is what a slide called wireless vulnerability, the very character that makes drone itself a useful, either relying on the wireless communication for control, navigation, and data transmission. Is also their greatest weakness. Every signal traveling through air or from a drone create a surface attack, the potential entry point for malicious. This includes the command link from the operator, the GPS signal, the GPS signal the drone uses for positioning, and the video feed it sends back to the ground. This vulnerability opens the drone to several different attack types. The slide lists the most common one, which includes spoofing, jamming, intrusion, and denial of service. Spoofing is an attack based on deception. A classic example is GPS spoofing, where an attacker broadcasts a fake, powerful GPS signal to trick the draw into thinking it is different location, allowing them to hijack its flight path. Jamming is a brute force attack where the attackers blast a powerful signal into the drone out the legitimate control signal, effectively serving the link between the pilot and the drone. Intrusion is a more sophisticated hack where an attacker exploits a software vulnerability to gain direct unauthorized access to the drone's onboard computer. A denial of service or DOS attack involves flooding the drone's communication channel with a junk data overwhelming its processor so it can no longer respond a legitimate command. The sequence of these attacks can be severe. In the worst case scenario, like a successful intrusion, an attacker would gain full system access, taking complex control of the aircraft and its sensor. Less invasive attack can lead a data compromise. A very sensitive information being collected by the drone, such as footage of an infrastructure inspection, is intercepted and stolen. At a minimum, attack like jamming or device will cause significant operation disruption, grounding a fleet of delivery drones to halt a critical service, to halt a critical survey mission, which can lead a major finance loss and safety risk. It is clear that cybersecurity is not just an IT problem for drone operators. It is a fundamental issue for safety and operational integrity. Given these significant threats, the industry is focused on developing robust countermeasures. A key part of this defense is creating an intelligent digital immune system for the drone network itself. Our next slide will look at how AI and machine learning are being used to power advanced detection system. After outlining the serious cybersecurity threat that drone faces, we now turn to the solution. A key part of the defense is to use drone's own intelligence against potential attacker. This slide focus on the use of machine learning and AI for intrusion detection system or IDS. Think of an IDS as a digital security guard, constantly monitoring the network for suspicious activity. This kind of advanced network protection is essential for remote ad hoc network, drone network. They are common in swarming application, and ad hoc network is one that is created on the fly between drone themselves without relying on fixed infrastructure like Wi-Fi router. These dynamic networks need a built-in intelligent security system to protect them. Traditional cybersecurity often relies on looking for unknown threat, much like an antivirus program scanning for known virus. However, attackers are always deploying new methods. This is where AI enhancement provides a massive advantage. Instead of just looking for a list of known attacks, an AI-powered IDS learns what normal behavior looks like on the drone's network. It analyzes the pattern of data, traffic, and communication to build a baseline. Anything that deviates significantly from this baseline is flagged as potential threat. This approach improves the system's robustness, resilience, and responsiveness. It is more robust because it can detect novel, never before even seen, making it resilient and able to respond in real time. A specific type of machine learning model often used for this is the LSTM RNN, which stands for long-term, long short-term memory recurrent network neural network. While the name is complex, the concept is intuitive. An RNN is a type of neural network that excels at understanding sequence of data over time, and the LSTM component gives it powerful long-term memory. The LSTM uh, RNN analyzes the data streams flowing through the drone's network in real time. It remembers the pattern of normal communication and use this memory to identify malicious pattern that might indicate an attack. It can detect a subtle buildup of denial of service attack or spot an unusual command sequence that signals an intrusion attack, flagging threat long before it do serious damages. In essence, an AI-powered IDS act as an intelligent immune system for drones network by using advanced neural network to learn normal behavior and spot anomalies. It provides the robust and responsive protection needed to secure the system. Detecting an intrusion is the first step, but a secure system also needs to control who can access the network in the first place. Our next slide will look at the role of machine learning in authenticating and accessing content.
Right. So, as we move forward, let's dive into the core of our topic, the fundamental innovation in drone design that are paving the way for the future. The slide gives us a fascinating roadmap to the key areas where progress is most pronounced. At the highest level, the entire evolution of drone technology can be understood through two powerful parallel forces: miniaturization and increased autonomy. These aren't just buzzwords, They represent the primary direction in which all the research and development are heading. First, let's talk about miniaturization. This is the relentless push to make drones smaller, lighter, and more efficient. We are moving from the larger aircraft-sized UAV that was once defined as the industry to device that can fit in the palm of your hand. This trend isn't just about making drone more portable or convenient. It's about opening up an entire new possibility. A small drone can operate indoor, navigate complex and cluttery environments, and be deployed more quickly and discreetly. It lowers the barrier to entry for business and individual, making the technology more accessible for a wider range of tasks. The second most major force in increased autonomy. This is a journey from a drone being a remote controlled puppet to become an intelligent, independent agent. Early drones requires a skilled pilot, constant attention to every moment. Today, we have features like GPS-based flight path and return to home features. The future, however, is about giving a drone high-level objective, like serving this entire farm of sign for crop stress and having it figured out the detail for itself. This involves planning its own flight path, avoiding unexpected obstacles, analyzing the data it collects in the real time, and makes decisions based on the data without human intervention. This is where artificial intelligence and machine learning comes uh, becomes absolutely critical. So, what's making this possible? The slide points to the key collaborator, advancement in sensor technology, actuator, and power storage. Think of these as the drone sensors, muscles, and stamina. Modern sensors are incredibly small yet powerful. We can now pack high resolution camera, thermal imagery, LiDAR, and a host of other sensors into a small frame, giving the drone a rich understanding of this environment. Better actuator, the motor and the control allows for more precise, stable, and energy efficient flight, which is essential for both navigating tighter space and excluding complex autonomous maneuvers. And finally, power storage. The battery has always been a drone's biggest limitation. The breakthrough in lithium polymer and other battery technology are extending flight time, allowing drone to fly farther and carry more, making them truly viable for demanding commercial application. These advancements directly fuel the expansion of drone application across numerous sectors. In the military, miniaturized drone provides critical intelligence without risking personnel. In agriculture, autonomous drone monitor vast area, applying water or pesticide with pinpoint accuracy, which improves yield and reduces waste. In logistics, companies are evolving the last mile of delivery, getting package to customer far and more efficient. And in the security, drone provides aerial surveillance for large facility or offer first responder crucial sky in the sky, crucial eye in the sky during emergency. As far you see, the key future trend are smaller size and great autonomy are not just separated by goals. They are deeply interconnected, each driving and enabling each other. The small drones need more autonomy to navigate its environment, and greater autonomy is made possible by the advances miniaturized component we have just discussed. In the next few slides, we are going to explore these two trends in much detailed manner, starting with the fascinating challenges and achievements in the world of miniaturization.
We have explored the incredible diversity in the drone hardware from tiny insect-like MAV to large versatile hybrid. The true revolution however begins when these individual aircraft stop acting an isolated platform and start becoming interconnected node in much larger digital ecosystem. This brings us to the crucial role of autonomous drone within the Internet of Things, or IoT framework. The Internet of Things is the vast interconnected network of physical devices, from smart sensor on fridge to thermostat in our home, all communication and shared data to create a more intelligent and responsive world. So, when do autonomous drone fits into the picture? You can think this of them as the ultimate IoT sensor, which while most IoT devices are stationary, drones are critical component because they can move through three-dimensional space to collect data precisely when, where, and when it is needed the most. They leverage their agility to navigate complex environment, positioning sensor in places that are dangerous, difficult, or impossible for human to reach. Furthermore, their ability to fly high above the ground level abstraction provides them with a significant advantage in the line of sight communication, making them highly reliable for relaying data in areas with poor connectivity. This mobility makes them exceptionally powerful tool for data collection, especially for large-scale environment application. As the slide notes, this includes environmental monitoring and air quality assessment. For example, a fleet of autonomous drones could be deployed over a large agriculture region to monitor soil moisture level, providing farmers with a precise irrigation instruction and conserving a mass amount of water. Similarly, drone equipped with specialized sensor can fly through an urban center to create dynamic 3D map of air pollution, identifying hotspot and providing city planners with actionable data to improve public health. This capacity extends directly into the realm of smart city application. A smarter city is one that uses interconnected technology to manage its resource and service more efficiently, and drones are becoming a cornerstone of this vision. They are invaluable for infrastructure monitoring. An autonomous drone can be scheduled to regularly inspect bridge lines and cell towers using AI-powered computer vision to detect small cracks, corrosion, or other signs of wear before they become critical failure. They also be used for energy efficient management. For instance, a drone with a thermal camera can survey a neighborhood at night to identify buildings with poor insulation that are leaking large amount of heat, enabling targeted energy safety initiatives. The OpenCV logo seen on the slide is a node of software that makes this possible. It is a computer vision library that helps drone interpret and understand the visual data they collect, turn it into a valuable information for the entire IoT network. In essence, the autonomous drone are the mobile intelligent eye in the sky for the intelligence of things. They overcome the limitation of fixed sensor by bringing powerful data gathering capacity to any point in the physical world. This idea of single drone acts as a node in the network is powerful. But what happens when we take it a step further? What if the drone themselves begins to form their own intelligence, a collaborative network? This leads us to one of the most exciting and futuristic area of drone technology, the use of drones. Now that we have set the stage, let's discuss the fundamental question. Why are drones or UAVs so important in the business world today? What is their commercial relevance? Image on the side provides a fascinating real-world example. We see a construction profession on a busy work site using a drone to get a closer, clearer overhead view of the project. This is a theme from the future that's happening every day on the job site around the world. This single picture perfectly encapsulates the core value proposition of commercial drone. They also allow us to work smarter, gather much information and safety and increase the safety. This is a practical reality of how this technology is transforming industry. The text on the slide highlights the UAV and becoming increasingly vital across a number of key fields. Many people associate drone with their military origins, where they are used for intelligence, surveillance, and reconnaissance mission to reduce the risk to human persons. This, their impact on the civilian world is now just a profound. In agriculture, drones are no longer novel. They are essential tool for what we call precise farming, helping to monitor crop health, optimizing irrigation, and improve yield. In the world of logistics, companies are heavily investing in drone delivery to solve the complex last mile problem, aiming to get package to consumer after a large efficient than ever before. And in the security industry, drones offer a powerful and cost-efficient way to monitor large property patrol parameters and provide aerial oversight during security operation. In all areas, UAVs have moved from being a nice to have to a need to have technology. It's also useful to think of a drone as the slide suggests as components of intelligence or support transport service. The drone itself is a transport mechanism, but what is transporting? What it is transporting? In many cases, it's not a physical package, but a sophisticated sensor package. This is where the intelligent part of the equation comes in. The data gathered by the sensor, whether it is high resolution imagery or the thermal data or a LiDAR scan, it is a real product. The data processed and analyzed to provide business and actionable insight or intelligence that was previously unavailable or too expensive to acquire. Because drones can be deployed quickly and economically, these intelligence services can be offered at a price point that matches them accessible to.
much wider range of companies and even individual consumer, democrating access to aerial data. The key driver of this accessibility has been the development of MAVs or miniature air vehicle. These smaller, often very portable drones have created an inexpensive platform for carrying powerful imagery technology. The slides mention electro-optical EVO and infrared IR cameras. EVO cameras are what we consider standard high definition visual camera, capable of capturing incredible detail photo and video for inspection or mapping. IR camera or thermal camera see the world in terms of heat signature. They allow them to identify issues which are invisible to the naked eyes, such as water leaks, faulty electronic components, or areas of crop stress. The capability to put these advanced sensors into the data for a fraction of cost of helicopter has been a true game changer. And this all leads to the final point. The collection of aerial data is enabling new business model and transforming traditional industry. Entire companies are now built around providing drone-based data service. Meanwhile, establishing industries like construction, energy, and insurance are fundamentally changing their workflow to incorporate the insight that this technology provides, leading to greater efficiency, enhanced safety, and better decision making. Now that we have established the legal foundation required to operate the drone commercially, the next critical step is choosing the right tool for the job. This slide introduces the most important principle in drone selection. The entire process is mission driven. There is no single best drone for every task. The optimal choice is always the one that is specifically tailored for the need of your mission and the environment you will be operating in. The drone that is perfect for cinematic photography might be completely unsuitable for long-range agriculture surveying. Therefore, we must begin by analyzing the mission requirement and then match a drone capability to those needs. Let's begin down the key selection factor you see listed here. First, we have range and endurance. This refers to how far the drone can fly from its operator and how long it can stay in air on single battery or tank of fuel. For mission that covers large areas such as mapping a coastline or monitoring a long pipeline, you would prioritize a drone with a excessive range and flight time. As the slide notes, this is where configuration like fixed wing aircraft often excel due to their aerodynamic efficiency. The next is payload capacity. The payload is anything the drone carries to perform its mission. This could be a high resolution camera for inspecting a multispectral sensor, for analyzing crop health, or even package for delivery. The weight of this payload is a crucial factor as it directly influences the required size, power, and cost of the drone. A heavier payload necessarily more powerful motors and a larger frame. This in turn impacts the drone's overall endurance and budget. The third factor is the drone's configuration. This is the basic design of the aircraft, and we'll explore this more in detail in the upcoming slides. The primary choice is between fixed wing model, which is like small airplane, multi-rotor model like the familiar quadcopter, or hybrid design that attempts to combine the benefit of both. Your choice will depend on whether the mission requires hovering stability, vertical takeoff and landing, or long distance efficiency. Finally, we have the practical consideration of cost and uh, complexity. The initial purchase price is only the part of the equation. You must also account for the total cost of the ownership, including maintenance software, insurance, and the necessary level of pilot training. The highly sophisticated drone must offer incredible capacity, but it also demands more significant investment in both money and skill development. Beyond the sport pillar, the graphics on the slide shows a host of other important features to consider. When comparing model, you will look at a specifically like the quality of the camera system, the maximum wind speed it can safely operate in, and its available smart flight mode and safety feature. For business factors like the availability of technical support, the length of the warranty, and even where the drone is manufactured can play a significant role in purchasing decision. To make the best choice, you must weigh all the factor against your specific mission profile. To help clarify one of the biggest differentiator, let's now take a closer look at different drone configuration, starting with fixed wing UAVs. Now that we have introduced the design philosophy of successive loop closure, let's look at the concrete example of how it is implemented. This slide details the structure of typical PID, lateral autopilot, which is responsible for controlling the MAV's roll and yaw motion to follow a specific path. The architecture is built around a fine inner loop and a slower outer loop. The inner loop is the roll altitude loop. As the name suggests, its inner loop controls roll angle, chi, and the roll rate, p. Its sole purpose is to achieve and hold a specific bank angle as quickly as accurately as possible. It uses the primary roll control surface, the aileron alpha, to do this. This loop runs at a very high frequency, constantly making tiny adjustments to make the MAVs stabilized at the commanded roll angle, detecting the disturbance from things like wind gusts. While commands to this inner loop is the course hold loop. This is the outer loop, and its job is to regulate course angle x. The course angle is actually directing the MAV is traveling over the ground. This loop is concerned with navigation, making sure the drone is flying towards its intended pathway. It achieves this not by controlling the ailerons directly, but by commanding the roll angle. For instance, if the autopilot determines that it needs to turn right to back on the course loop will simply send a command like roll to 20 degree to inner roll altitude loop. The fast, stable inner loop that executes this command precisely. This separation of duties is the essence of successive loop closure. For some more advanced fixed-wing aircraft, an additional optional loop might be included as side slip hold. This loop's purpose is to ensure the aircraft is flying cleanly through the air without skidding sideways. It uses rudder delta R to maintain zero slip beta if equipped, resulting in a more efficient and coordinated run. By layering these simple controllers, we create a highly efficient system. As the slide concludes, the nested loop structure provides stability and robustness against disturbance while maintaining desired flight path. A fast inner loop handles the immediate stability, while the slower outer loop focuses on the overall navigational goal. This elegant design simplifies development and tuning and results in a very robust autopilot. Just as we use a nested loop structure for a lateral control, we apply the very same design principle to manage the aircraft's longitudinal motion, that is, its pitch, altitude, and forward speed. This slide breaks down the components of typical PID control for longitudinal autopilot. The architecture is once again built around the fast inner loop and the slow outer loop, as shown in the block diagram. The foundation of longitudinal stability is the pitch altitude control loop. This inner loop controls pitch angle theta during the elevator. Its one and only job is to hold the aircraft nose at a specific pitch angle that is commanded by the outer loop. It runs at high frequency using the elevator to make rapid adjustment to maintain this angle, thereby providing the core pitch stability for the MAV. The next layer of control is the altitude hold using commanded pitch loop. This is the outer loop, and its purpose is to regulate altitude H by commanding pitch theta C. This is a perfect example of successive loop closure. If the autopilot determines that MAV is below its desired altitude, this outer loop doesn't command the elevator directly. Instead, it calculates the required nose up pitch command and sends that to the inner loop. A fast and stable inner loop then takes over to execute the command, causing the aircraft to climb. Controlling airspeed is bit more nuanced as the relationship between pitch and throttle changes depends on the phase of the flight. There are different airspeed control methods. Often, the autopilot is using commanded pitch theta c in climb and descent zone to manage speed while setting the throttle to full or idle. Conversely, it will be using throttle delta t in altitude hold zone to regulate speed, while the pitch is being used to maintain constant altitude. When designing uh, and tuning these nested PID loop, engineers must consider several key design parameters. These include actuator saturation limit, a desired damping ratio, to control the responsive and principle of bandwidth separation to ensure the inner loop are always significantly faster than the outer loop they support. Hope that we laid the foundation and explored the challenge of motion planning, it's time to dive into some of the advanced algorithms that are used to tackle these problems in practice. They are not just theoretical tools, they are the core techniques that allows micro aerial vehicles or MAV to autonomously navigate complex environments. Think forest, urban canyon, or cluttery outdoor space. Let's begin with the classical approach that has been around for some times, yet still holds strong in many path planning applications. Voronoi graph. Let's start with the concept. Voronoi graph works by dividing the environment into convex region or cells. The edge of the cell are positioned exactly halfway between the obstacle in the environment. Think of this way. Imagine you are in a field full of rocks. Obstacle. If you were to draw a line such that every point of the line is the same distance from the two near rocks, you will end up with something like a Voronoi diagram. The result is a network of paths that maximize the clearance from any obstacle, which is very desirable property when you are flying a drone through tight space. Technique is particularly useful in uh, con- congested, particularly useful in congested environment. For example, in airspace with a lot of point like obstacle, like trees or towers, because it inherently find the safest possible path. It is well suited for scenario where obstacle avoidance is the top priority. Next, we'll look at the most modern and widely used algorithm, especially in robotics and algorithm and autonomous vehicle, the Rapid Exploration Random Tree or RTT, RRT, Random Tree or Rapid Exploring Random Tree. So, what is the big idea behind RRT? The core concept is that sampling based algorithm rather than exhaustive search the entire space, which can be computationally expensive. The RRT randomly samples the environment and builds a tree of possible paths. Here's how it works. First, the algorithm picks a random point in the space. Then it finds the closest node in which the current tree of known path. Finally, it extends the tree a small step towards that random point. This process is repeated again and again, rapidly growing a network of paths from the start location. Over the time, one of the branch will likely connect with the goal region, providing a feasible path. What provides what powerful about our RRT is how quickly it can cover a large complex space, especially when compared to deterministic approach. However, the trade-off is that the path it finds are often rough or inefficient. The next method uh, is the RRT's extension. To deal with those jagged, less that ideal path, we
turn to extend post-processing technique. One key extension is called path smoothing. After RRT find a valid path, path smoothing is applied to remove unnecessary immediate points. This makes the route shorter, cleaner, and more efficient for the drone to actually follow. Without smoothing, the drone might be making constant sharp turns, which isn't ideal for flight stability or battery life. Another important extension, especially relevant for MAV's operation in the outdoor environment, is the 3D terrain planning. Instead of planning it in a flat 2D space, this technique allows us to extend RRT into 3D, taking into account altitude variation and terrain constraint. This is essential when navigating over hills, building, or through valley. The algorithm ensures that the waypoint are chosen that the MAVs maintain safe and efficient flight in a vertically varying environment.
We have discussed the general commercial adoption of the drone, and now we'll dive into one of the most valuable and impactful use case, the innovation in infrastructure and inspection. The drone are fundamentally changing how people monitor and maintain critical backbone of our society, from our power grids to our cities. A primary example of this transformation is in power line assist. Traditionally, this has been slow, dangerous, and expensive task, avoid often requiring ground crew to traverse difficult terrain or using costly unmanned helicopter. The drones have then introduced an autonomous real-time monitoring approach. An autonomous drone can be programmed to fly along hundreds of miles of transmission line using its onboard sensor to scan for any signs of damage or wear on the cable, insulator, and tower. This allows utility companies to identify and fix potential points of failure before they can cause a major power outage. This powerful inspection capacity is made possible by the suite of advanced sensors. These drones can carry, for instance, thermal camera can detect overheating component, which are key indicator of an immediate failure. Ultrasonic sensor can pick up on a high frequency sound associated with the electrical arcing, which is invisible to the naked eye, and of course, high resolution visual camera combines with AI-driven image processing can automatically spot physical defects like rust or vegetation that has grown too close to the line. The construction industry has also been a revolution by capacities. Prawns are now a standard tool for major building projects, providing a value throughout the entire life cycle. At the beginning, they are used for initial site survey, creating a high accuracy 3D map of the land, including the project. They are used for assessed inspection and most importantly for daily progress tracking. By providing a daily eye on the sky, the drone gives a project manager a real-time view of the progress, allowing them to compare the work on the ground to digital blueprint, which help them to keep these massive projects on schedule and on budget. This ability to monitor and manage the infrastructure of our world is making our industry safer and more efficient. And while our focus is on this slide, we'll be inspecting the image points to another major drone application in our cities in drone delivery. These two concepts are inter- interlinked. The same drone that inspects a building front gate today may be delivering a package to its rooftop. And we have completed our drone technology. And thanks everyone for watching and hope you had a great session throughout this entire unit. Thank you all.